Hello, Applied Physics. Today we're going to be talking about light waves. So last week we talked about sounds. Now we're going to be moving on to light and how light can act as a wave. Before we get into that, let me just go through some quick learning goals here. First learning goal is that you can understand and label the basic parts of a wave. So we've been doing that for at least 1 or 2 weeks now. We've been labeling waves so you just understand the basic components. We'll do a quick review though. I can explain you can explain the main components of electromagnetic wave. So we'll explain what electromagnetic wave is, how it is related to light. I can explain the major parts of the electromagnetic spectrum. So again, we'll talk about the electromagnetic spectrum and what some of the major parts are. So let's go do a quick review about waves. So on the left side here, you got your basic wave diagram. So the top of a wave is called the crest, the bottom is called the trough. The distance from, or sorry, the height of a wave, or you can even say the depth of a wave, is the amplitude. And the distance from crest to crest or from trough to trough is called the wavelength. And the last thing we talked about was frequency. Frequency is the number of wavelengths that pass over a given time. In this little animation here, you can see that the red line, or sorry, the red wave has a longer wavelength, a larger wavelength, which means it has a smaller frequency because there's fewer wavelengths passing over a given amount of time. The blue wave down here has a shorter wavelength or a smaller wavelength, but it has a greater frequency because there's more wavelength passing per unit time. So frequency and wavelength are inversely related. The bigger the wavelength, the shorter the frequency, and the shorter the wavelength, the larger the frequency. And so here's another example of waves here. So here we have the transverse waves. Transverse waves are a lot more easier to understand than the longitudinal waves. So remember, this is kind of what sound waves looks like. Sound waves are best represented by compression and decompression. So these dark black bands are like the compressions of a sound wave, and the white area in between is like the decompression. And we can represent that, the compressions and decompressions, by the crests and troughs of a transverse wave. So here's one with high frequency, low wavelength, and on the right side do we have, or I'm sorry, on the left side, low frequency, high wavelength, right side, short wavelength, and high frequency. So same concept, just a little more complicated animation there. Okay, so let's talk about light waves. So anytime you hear me say electromagnetic wave, I'm talking about a light wave. Why are light waves called electromagnetic waves? It's because light waves are made of electric and magnetic fields. If you ever go into engineering or any kind of advanced physics, you will learn that any moving electric charge has a magnetic field, and any magnetic field has an electric charge. It's just they're kind of bound together. So when you have a moving when you have a electromagnetic field that's moving, well, that manifests as an electromagnetic wave or a light wave. Again, electromagnetic wave, light wave, it all means the same thing. So whenever you see that word electromagnetic, just think light. But it is the reason that we use this word electromagnetic wave instead of just light wave is because light is a lot more complicated than just the visible light. But I'll touch on that more later. So this is what an electromagnetic wave might look like. Of course, electromagnetic waves move much faster than this, and the wavelength is not always the same. This is a pretty large wavelength for even if you're looking at this on your phone. This wavelength is pretty large for your ordinary kind of light wave. This would probably not be visible to your eyes if that were the true size. Anyway, so let's talk about what these components of the waves actually mean. We talked about this with sound. Let's compare this to electromagnetic waves or light waves. So the amplitude is the height of the crest or the depth of the trough. For a sound wave, amplitude meant the loudness. So the higher the amplitude, the louder the sound wave. Electromagnetic wave is the brightness. So the brighter something is, that means it has a higher amplitude in the wave. For sound, the frequency or wavelength, if you change the frequency or wavelength of a sound wave, you change something's pitch. Remember when we did the sound labs, something that had a really low sound, what has a really large wavelength or a low frequency. Something really high had a high frequency or short wavelength. Well, for electromagnetic wave or light wave, I'm gonna stop saying that. Electromagnetic waves, the frequency or wavelength changes the color of the light wave or the type of light wave. And so what do I mean by type? Why can't I just say color or type? Why can't I stick to one or the other? Well, it's because when it comes to light waves, we cannot see all the different colors or types of different light that are out there. Um, our eyes are only designed to capture certain frequencies of light, and our brain tries to make sense of those frequencies by showing our consciousness colors, which is a whole different topic for a whole nother discussion. That's just kind of how eyes work. We can't see all the light that's out there. In fact, to kind of show you what other light is out there, I have to show you this diagram, the electromagnetic spectrum. I'm going to show you this diagram again in a couple of slides with a little more detail added. So these are all the major components of the electromagnetic spectrum. You got the very low frequency or high wave or long wavelength, you have radio waves. Then a little higher frequency is microwaves, then infrared waves, and then this little short band right here is the visible spectrum. Moving on, we have ultraviolet waves, X-ray, and gamma rays. But so everything our eyes can see is only a very, very small fraction of all the different types of light that are out there, which is kind of crazy to think, but our eyes are really only designed to see that part of the electromagnetic spectrum, which is good for us because sunlight peaks right in the middle of the spectrum, right around that yellow-green area. That's the majority of the light that comes from the sun is that yellow-green light. So just to kind of show you how small this band is, this actually is not to scale. This is a logarithmic scale, which means instead of advancing by ones, it advances by tens. I'm not going to explain what logarithmic scale is, but this visible, even though that this is a very small band of visible light here, actually, and if you were going to compare this to the actual electromagnetic spectrum, it'll be a little punier. Let me show you by this example here. If we stretch the electromagnetic spectrum, in other words, if we stretched all the possible colors or types of waves that are in the electromagnetic spectrum from all the way from LA to New York, the amount that we would be able to see is the width of a thread. So we can only really see a very, very tiny part. And obviously this thread is not the scale. There's no piece of thread that's this big. But if we could put a piece of thread somewhere in Nebraska or Iowa or whatever, that is the approximate size or ratio of wavelengths that we could see compared to the rest of the electromagnetic spectrum. So let me go back to the electromagnetic spectrum and just talk about the different types of wavelengths or frequencies that are out there. So this is a pretty cool infographic on the electromagnetic spectrum. On the top here, what this is showing if we had a light wave that was this big, the size of a building, well, this is what kind of wave we would have. We would have an AM radio wave. So when you turn on your radio in your car or home or whatever, and you tune into AM stations, those radio waves have wavelengths that are the approximate sizes of buildings. One thing I didn't go over is the speed of light. The speed of light, which is in CK12 chapter today, I know, it is 300 million meters per second. So the reason you can receive those AM radio waves, even though they're as big as buildings, and the reason why your radio can make any sense out of them is because those waves are traveling so fast they can still carry a lot of information because they're moving so fast. And going up, you got if you go to the size of humans, now that's about the size. Those microwaves are about this carry the energy of microwaves. So your microwave ovens use something called microwaves. That microwaves are part of the electromagnetic spectrum. So when you cook your food in a microwave oven, you're actually using light, not the kind of light that your eyes can see, but something with a much larger wavelength that can cook your food. And notice that I put this little cell phone here because cell phones actually also kind of fall in between this radio microwave range. Your phones use a frequency that's very similar to microwave ovens. Does that mean you're cooking your brain? Well, probably not. But I mean, there if you talk on the phone a lot, it's um, there is still a tiny. You're still receiving a tiny bit of microwave radiation. Um, so, and then moving on, you have radar. This is still in the microwave radio range. Radars that are used to track planes use that almost the same type of frequency that microwaves would use. Um, then the next one after microwaves is infrared. So now we've gone from light waves that have the wavelength the size of buildings to humans to butterflies to a point of a needle to protozoans, which are basically like little cells or bacteria. I'm sorry, I'm not a biologist, I'm not sure, but protozoans. So light that has the wavelengths of something that's very tiny produces infrared light. On down here, it says the source of infrared light is humans. So it's not trying to show you the size, it's showing the source. So what this is saying is that infrared light, when you think of infrared light, think of heat. You put your hands up to a fire, you feel that heat. You put your hand up close to a hot stove burner, that is infrared light. So whenever you have that feeling of heat radiating off of something, in fact, if you have a radiator in your home that's used to heat up your home, that's also uses infrared light. The reason it shows us humans down here, anything that is warm will produce some sort of heat. So your body right now is emitting light, like just like a light bulb emits light. Your body is emitting light just because you have an internal body temperature. The average internal human body temperature is around 98, 99 degrees Fahrenheit, and so that temperature produces infrared light. Now, on the other hand, the sun is so hot that it burns yellow white. It's so hot that it doesn't produce infrared light. It doesn't produce red light. It produces a yellow white light. So um, we'll probably talk more about that later this term about thermodynamics. But just want you to know that the infrared light is talking about that heat that lots of natural bodies give off. So moving on, after infrared, you have the visible light spectrum, which is everything that we can see, the whole rainbow, Roy G. Biv, excuse me, Roy G. Biv, red, orange, yellow, green, blue, violet, right? When we get down to light that have the wavelength the size of molecules, now we're getting really tiny. Then we're talking about ultraviolet light. And ultraviolet light can, excuse me, we use ultraviolet light in lots of applications to sterilize things. Ultraviolet light also comes from the sun. That's what gives you sunburns. And if you have to catch too much ultraviolet light, you can start developing skin cancer. Which is why if you get, you need some sunshine to produce vitamin D in your skin. But too much sun exposure will give you sunburns. And if you have too much sunburns, you'll get skin cancer, which is why you are recommended to wear sunscreen whenever you have long days at the beach or something like that. Moving down from the scale of molecules to atoms, and there's a difference there. I don't know if you guys are taking chemical systems or not, but atoms are much smaller than molecules. Now we're getting down to X-rays. So let me stop at X-rays for a second and just talk about um, the harmful level of light waves. So I talked to you about how too much ultraviolet light can be harmful to you. Really, any light in this on the electromagnetic spectrum, all the way from radio all the way to gamma, can be harmful to you if taken in the right dosage. Um, like I said, cell phones use a tiny bit of microwave radiation. That's not going to kill you right then and there. But if you, you know, if you're if you're exposed to an open microwave oven, yes, that will cause you to experience pain or maybe cancer or something like that. Um, Same with infrared light. Infrared light is basically just heat, right? Too much exposure to heat will hurt you. Even visible light, if the visible light is bright enough, it can hurt you. It would take a lot, but it could hurt you. So all of these light waves are harmful in some ways. However, the higher you go up on the electromagnetic spectrum, the lower doses you need to actually hurt you. So ultraviolet light is harmful because it can burn your skin more readily than visible or infrared light. Uh, X-rays is higher up on this spectrum, which means it has a smaller wavelength and a higher frequency. With light waves, frequency is related to energy. So X-rays are harmful to you. If you ever go to get an X-ray, they'll put you behind a machine while the doctor stands behind a big LED screen, or maybe puts a LED vest over his chest. Or if you even go to the dentist, you might notice the dentist tries to keep his or her distance from you when they take the picture of your teeth. That's because those people have, if they did not do that, they would have exposure to X-rays every single day, and constant exposure to X-rays is not good for you. You can get um, radiation sickness or disease that comes with that. So the way that X-rays works, that X-rays are so tiny. Remember, we're talking about wavelengths the size of atoms now. That's the wavelengths are so tiny that the X-rays pass straight through your skin, but they're not energetic enough to pass through your bones. So the way that the X-ray cameras work is that one, you have something emitting X-rays and then something on the other side catching the light, and so your what's left behind is kind of like the shadow of what your bones and stuff are. Um, the most energetic light electromagnetic waves are gamma rays. So X-rays are strong enough to penetrate your skin but not your bones. Gamma rays are strong enough to penetrate anything, even up to several meters of cement. So gamma rays are very energetic, very powerful. Um, Lots of cancer treatments are based on um, that kind of radiation, which is why it has to be taken in small doses and has to be very carefully monitored. Um, so that is the electromagnetic spectrum. Whenever you hear electromagnetic spectrum, we're talking about all the different types of wavelengths that light has. And it's not really fair to call these colors because these aren't really colors. You can call them flavors or types or whatever, but the only colors that human eyes can see is this tiny sliver of the visible light. And I talked about how insignificant the visible light is compared to the rest of the types of light. And then what's pretty cool to know is that some animals can actually see in the infrared range or the ultraviolet range. And of course, we have instruments that we can detect any kind of waves. Obviously, we have instruments that can detect radio waves. That's how we communicate and use radio stations. But we have instruments that can collect any kind of um, radiation. So that is your introduction to the electromagnetic spectrum. So again, we first objective, you can understand and label the basic parts of a wave. We reviewed that. You can explain the main components of electromagnetic wave. We explained how frequency or wavelength is related to the type of electromagnetic wave. That was, which is like the, or I'm sorry, how the frequency and then the amplitude of the wave was related to brightness, and the major parts of electromagnetic spectrum that you can explain. We talked about the radio waves, microwaves, um, uh, gamma rays, X-rays, ultraviolet light, and invisible light. I'm not expecting you to necessarily memorize the different parts of the electromagnetic spectrum. Um, not don't want you to memorize the order, but I do want you to recognize that all those parts are basically light waves. If you could take a light wave in your hand and you could stretch it, you would be lowering the frequency, um, and you would be changing like maybe visible light to a radio wave. If you could compress it, you can change it all the way to visible light and maybe into X-rays or gamma rays. So that's the idea behind the electromagnetic spectrum. But so I'll make sure that you guys have some more resources. I know I've already found some more infographics I think are pretty cool. and just go through your CK12 reading. If you have any questions, let me know. Hope you guys have a good day.